Hi Year 12, welcome to our A-level computing lesson on representation of negative numbers and fractions using binary. And just before we start, in terms of where we are in the spec, we're looking in 1.4 now for a few lessons. And this is something that we'll be doing some of the work from this topic this year, and some of these are Year 13 topics. So we won't be covering all of it by any means. And with regard to today's content, if you want to access anything that I've used today, if you go to the revision site, I've already uploaded the presentation that we're going to look through on there, as well as the questions and exercises from the lesson are underneath there as well. So there's plenty for you to use to reflect on today's content. So we'll get started on the actual lesson itself. And before we start, I think it's important just to consider the prior knowledge that you're going to need. In other words, what you need to know coming into this in order really to be able to understand this topic. I won't read it to you because you can see what it asks for there, but basically you need to be comfortable with binary and hex, really up to the level that you did it at GCSE. And if you aren't comfortable with that, you might want to go and look at some of the AS work that we've posted on Classroom earlier, and you might want to maybe look back at some of your GCSE stuff as well, because this was all covered there. So you should be okay with addition, binary, hex conversion, the reasons why we use hex, etc. So if you're okay with all of those topics, then we'll carry on and we'll get started. So the outcomes from today, what we need to be able to do, several things. Understand the use of something called sign and magnitude in binary representation. We need to know about something called 2's complement as well. Again, two terms that you won't be familiar with. Don't worry, you will understand them by the end of this. Being able to perform subtraction using 2's complement. So you may already be able to perform binary addition, but we need to look at how subtraction works. And finally, the use of something called fixed point in binary numeric representation as well. So this is what I'm hoping to cover. So we're going to begin with a question, and you might just want to pause the video and have a little think about the answer to this. Knowing what we know about binary, or what you understand so far about binary, if we wanted to write a machine code program in which we would store weather data, so we were going to need to use binary in order to do this, what kind of a problem might we have? So you might just want to pause the video and think about that for a second, and then we'll look at the answer in a moment. Okay, so the problem that we'd have, if you hadn't already worked it out, was that we would be needing to use non-integer and negative numbers. So probably so far in binary, you've only really looked at representing whole numbers, first of all, and numbers that are positive. But weather data is an example, and there's many other examples where this is the case, where a computer might need to store numbers which aren't integers, so real numbers, float numbers, or negative numbers. So at the moment, we do not know how this system works, how we can use either non-integers or negative numbers in binary. So we're going to look at a couple of ways in which we can solve this problem. So the first method we're going to look at is something called sign and magnitude. And to begin with, let's just look at how we're used to seeing a binary number. So this is what you're hopefully now comfortable with, the idea of 8 bits, starting with powers all represented each place in powers of 2, starting at 1 and then finishing with 1 to 8. And we know that by changing each one of these bits to a 1 or a 0, we can produce a different value. In fact, we can produce any value in the range between the ranges of 0 with all the bits switched off and 1 with all the bits switched on. So 0 from 255. So 256 values in total. Hopefully that's something that you're used to and are comfortable with. With sign and magnitude, though, we can find a way of representing negative numbers, because currently with this method there is no way at the moment of showing a negative number in 8 bits. So the solution is to change how we use these 8 bits. So we're not increasing the number of bits, we're going to change how we use them, or rather how we use one of them. So instead of representing the entire value of the number in all 8 bits, we're going to use the left-hand bit, what's called the most significant bit. We're going to use that bit to represent the sign of the number. So a number can either be positive or negative. So the value of that first bit dictates whether our number is positive or negative, and the remaining bits are used to represent the size or magnitude of the number. So that's why this method is called sign and magnitude, because one 8-bit number contains both the sign dictating whether it's positive or negative, and the magnitude dictating the size and the value of the number. So in our most significant bit in this column, we can still only store a 0 or a 1, but we use, if it's set to 0, that means that the number is a positive number, and 1 means that we've set it to a negative value. Okay, and then the remaining bits, as we've said, are used to dictate the value or the magnitude, the size of the number itself. So using this example, I've written 2 binary numbers below, and again, this is a situation where you might just want to pause it to have a little look at this question. What would the value of the 2 numbers be below if we're using the sign and magnitude system? So just have a little pause the video, perhaps see if you can work out what you think the numbers would represent. Okay, so the first number would be 28, positive 28, because we know this. If we look at where the bits are set, 16 and 8 is 24, and 4 is 28, and the sign bit is set to 0, which tells us that it's a positive 28. The same bits below are set, but this time it's minus 28 because we've also set the value of this bit to 1. So you notice how both of these numbers are identical except for the use of the sign bit in the left hand column in the seventh bit. So that's a really straightforward way of representing a negative number. Again, I'm going to ask you a little question. Using this method is lovely and simple, so there's a positive and an advantage, but can you see a problem with using sign and magnitude to represent binary numbers? And again, this is a good chance to pause and just have a little think. Looking at that system above at how sign and magnitude might work, can you see a possible problem? Well, let's have a look at the answer to that. So here is our sign and magnitude binary system again. Again, look, we've got our 7 bits representing the magnitude and 1 bit representing the sign. The problem is that we now only have 7 bits available in which to store the magnitude of any number in binary form. So that changes the smallest and largest numbers that we can store using this system. So what do you think the smallest and largest numbers are that can be represented using sign and magnitude? Again, opportunity to pause and have a think. Okay, so there's your answer, 127 and minus 127. And the reason for that is that if we turn all of those bits onto 1, 64, 32, 16, 8, 42 and 1, we end up with 127. And then that's either going to be a positive with a 0 at the front or negative with a 1 at the front. So using that bit to 1 doesn't give us 255, it gives us 100 minus 127. So it affects the size of the values that we can represent, and you can see how in a computer that might be a substantial problem. So let's have a look at another possible issue as well. Let's go and have a look at some addition. So we've got here 2 binary numbers. We've got first one, hopefully you can work out that that is negative 100. And then underneath, what we've got is positive 108. Okay, so what they represent, the first one represents the balance of an overdrawn bank account, So somebody has got minus £100 in the bank. And in the second value represents the amount that's actually going to be paid in. So it's a very straightforward calculation I'm asking you to do. Basically, you know in real life that if you added £108 to minus 100, you would hope to end up with a balance of £8, wouldn't you? So see if you can do this addition in binary and see what you end up with. So definitely pause the video here, carry out this addition using the rules of binary that you're used to, and see what answer you manage to get. Well, hopefully this is the answer that you've got, and you can see straight away that we've got a problem. And the problem is immediately apparent from our left hand digit because it's a 1. We've added, remember we started out with minus 100 and added 108 to it, so we should have a positive number. So we know right from the word go that we've got a problem and that hasn't worked. I wonder why that is. What is wrong with this method of addition using these two numbers that means we come up with this problem? The problem is that using sign and magnitude for negative numbers, we can't perform addition or subtraction as we might normally do. The reason is this left-hand digit, because we've treated that as a numeric value. We've treated that as a power of 2, and that's affected the result of the number that we've got. Remember though, in sign and magnitude, this doesn't represent part of the value. It only represents a sign, whether the number's positive or negative. So we can't use that in an addition because it's not actually part of the number. So we have a problem. We need to find another way, perhaps, of representing negative numbers, which will allow us to avoid this difficulty. So we're going to look at our second method now of representing negative numbers in binary, and that's going to be something called 2's complement. So before we move on to the second part of the lesson, make sure you're comfortable with what we've done here. If you need to skip or we go back to the beginning and flip through some of this again, feel free to do so, and then join us back at this point in the lesson if you're happy with what you've done so far. Still with me? Great, let's carry on. So 2's complement. This is an alternative method of representing binary numbers, and it's one that we're going to be using more extensively in year 13. So what we're going to use as an example, first of all, to introduce it to you, is the idea of the concept of an odometer in a vehicle. An odometer is just a fancy name for mileometer. So when you buy a new car straight from the factory, its mileometer, its odometer is set to 0 because it's obviously travelled no distance. If that was driven, for instance, a mile from the factory to the showroom, and we turned it forward 1 mile, our odometer, our mileometer would be 0.00001. Straightforward because we've just added 1. But what would happen if we were actually to turn the odometer back 1 mile? So if it started at 0, but we actually rewound it so that it went back, what would that value look like? You've probably all seen a dial like this before, if you've not on a mileometer. So just what do you think that would look like? Just a quick second to think of that. Well, this is what you'd get. So this is what we get to start with, our starting value. This is what we get when it moves forward. And this is what we get, and I've kind of spoiled my answer for the next bit. This is what we get if we wound it back 1. So 999999 would actually be the equivalent, wouldn't it, of -1. Okay. So what this is a kind of a little example of how the concept of 2's complement actually works. So in 2's complement, we have a slightly different system. Here is our 8 bits again. And this time I've highlighted red again, the most significant bit, bit 7. You can see I've numbered the bits starting out with bit 0 from here all the way down to bit 7 here. And bit 7 is minus 128. Okay. So it is something that it maintains its numeric value, but so we can use it as part of our number, but it's also set as a minus value. So below we can see the smallest and the largest numbers that we can represent in this format. Now we still have a slight problem in terms of the size of the number that we can work with in 8 bits, but for the moment we're not particularly worried about that. So an 8-bit number would look like this. So you would have minus 128 by setting that bit to 1, and then the rest of the bits to 0, and positive 127 by setting that bit to 0 and the rest of the bits to 1. So that gives you the idea of the range. Don't worry too much for the moment about the range. So if we wanted to represent 88 as a negative number, this is how we would do it. So we would start out with, if it's 88 and it's a negative 88, we know straight away that that left bit has to be 1 because we want a minus number. So we've got minus 128. And to get that number to 88, we add 32 to it, and then we add 8 to it. So if you have a calculator and you sit and work that out, you'll see that minus 128 plus 32 plus 8 equals 88. Okay, or minus 88. So just have a little look at that for a minute and make sure that that makes sense to you. It's just normal maths. We're not changing the way maths works or the positive and negative numbers work. You know that if you add positive numbers to a negative number, you make that number bigger. So what you need to be able to do at A level is you need to be able to convert a binary number into a 2's complement binary number. Okay, and that's easy to do, and there are 3 steps. Okay, and it might sound tricky, but we're going to do an example, and then once you've understood this method, I'm going to show you a really easy method. So the first thing we do is we start with whichever number we're working with as a positive binary number. So in fact, what this should say at the top, convert a decimal number into a complement binary number, not a binary number. So if we were taking like in this example, minus 9, the first thing we would do is write this down as a positive binary number. So we'd end up with 9 in binary. Then, starting with bit 0, so starting from the right, we copy all the bits up to and including the first set bit. And what that means is, starting from right to left, the first bit in that number, which is a 1, is the first set bit. So going from right to left. And then we invert all the others. That sounds really confusing, but it isn't. Hopefully, we'll see in a minute. So if we're going to represent minus 9, let's have a look and see how we start. So first of all, we write 9 as a positive binary number. So no change there. That's how we're used to writing 9 in binary. That's fine. The second thing we do is we, starting with bit 0, copy all the bits up to and including the first set bits, and we get rid of the others. So if you look at this, if we start from right and move left, the first bit in bit 0 is 1. It is set. So we take that one and we just get rid of all of the other bits for the moment. We just clear them. We're going to put them back, but for the moment we just clear them. And then we reinstate them, but we invert them, we switch them about. So in this position, bit 1 would be a 0 in our original number, so we invert that and it becomes a 1. Bit 2 would be a 0, so we invert that, and it becomes a 1. Bit 3 is a 1, and we invert that, and it becomes a 0. And then all our remaining bits weren't set, so effectively that means it was 0. So we invert those 4 bits, and they become 1. I'll go through that just very quickly again. And if you're happy with this, you can just skip forward and carry on with the video, but it might be helpful for me to show you again. So not -9. So we begin with forgetting the minus and just writing the number down as 9 in binary. Yeah, like that. And then we start from bit 0 and look for the first set bit in the number. So going from right to left, we look for the first bit that has a value of 1. And that, in the case of 9, is the very first bit. In fact, for any odd number, it's going to be the very first bit, isn't it? That's the bit that's set if we have an odd number. And then we get rid of remaining digits. So they've all gone. Then what we do is we put them back, but we invert them. So looking at our original number of 9, we've kept the 1, we flip 0, so it becomes 1, we flip 0, so it becomes 1, we flip 1, so it becomes 0, and just fill from blank, and we have 4 ones. So we end up with this number here as our binary number. So why don't you have a go at this question here? Can you use this method to represent the number -14 in 2's complement binary? Okay, again, it is a good point to pause the video, and then I'll go through the answer with you, and you hopefully manage to get it right. So pause now and have a little go at that question. Okay, so we're going to go through the answer. So the first thing we do, we've got -14. So the very first thing we do is we take the number and we represent it as a positive binary number. So that's what 14 looks like as a positive binary number. That's what we should be used to. Then we work from right to left, and we keep going until we reach the first set bit. So if we start at 0, the first bit we come to is 0. So that bit isn't set. So then we move one bit to the right, sorry, to the left, and we come to a 1, and then that bit is set. And now what we do is we invert the remaining numbers. So you can see that those 2 1s become 0s, and because those bits weren't set, those become 1s. So we end up with those 4, with that as an answer. There is an easier method for 2's complement conversion, and I want you to make sure you understand the other method so you actually understand what you're doing, but this is a much easier method. Basically, start with positive binary, invert each digit and add 1, and that's it. Really, really straightforward. So you turn the noughts to ones, the ones to noughts, and then you add 1. It is an absolute doddle. So if you try it on this number, -77, positive 77 looks like that. So then if you invert it and add 1, it works with that. So you can turn them all the ones to noughts and once, then add 1 to the number, and that's super straightforward, hopefully. Okay, so you might just want to spend a minute to write that down. Try that yourself, and then if you're okay with that, we can move on. So if you want to turn it back to denary, invert each digit again and add 1. And I'm just pausing so you can take that in. So whereas the idea of negative numbers in binary might have seemed terrifying at the beginning, hopefully you can see that 2's complement is actually really straightforward. It's not difficult at all, and certainly the noughts to ones, ones to nought method is one that works really well. So what we can do now is we can actually use 2's complement to perform arithmetic, and it's much more straightforward doing arithmetic in 2's complement, and we'll see why. So if we want to add, if we want to do addition, addition works exactly as normal, and subtraction, all we do to actually subtract, we just do an addition again, but we take the second number that we are doing and we make it negative. And then we add that negative number to the first number. So in other words, if we wanted to do 18 minus 9, instead we would do 18 plus minus 9. Yeah, and you don't have to be a maths genius to see that works in exactly the same way. So let's do 18 minus 9 as an example. So there's 18, okay, there is 9. If we want to turn 9 into minus 9, that's what it looks like. So we turn the noughts to ones and the ones to noughts and add 1. So we end up with that as our minus 9. So then all we need to do is add this number to this. So two numbers together. It's not lined up brilliantly, but again, this might be a good time to pause and try and do that addition yourself. And you end up with that. And then what we do is we lose the leading one. We lose the one on the left-hand side there. But you can see if I get rid of that, what I've done is I've ended up with 9, or you hopefully ended up with 9, and indeed 18 minus 9 is 9. So hopefully you can see how that works. And that's now binary subtraction using 2's complement, and that's how it works. And I'm going to set you some bits to practice that with later on at the end of this session. So that's our second kind of main bit that we needed to do in terms of second and third that we needed to do in terms of our learning outcomes. We've looked at now how 2's complement is used to represent a binary number, and we've looked at how we can perform subtraction by adding a negative 2's complement number to a positive number. So we can now move on to the final part of the lesson, which is looking at the idea of binary numbers to represent fractions. And again, this is fairly straightforward. So we can represent fractions in binary, and there are different ways of doing this. The simplest is fixed point binary. There is another method of doing this called floating point binary, but we won't be doing this in year 12. That's A-level work, so don't worry about that method for the time being. So here again is our 8-bit binary number, and this time you can see, hopefully, that we've split it into two groups of 4, so 4 nibbles, 2 nibbles, essentially. So notice that the positions to the right, that the digits to the right of the binary point, notice I'm calling it a binary point, not a decimal point. The numbers to the right are fractions, yeah, starting half, and then each time getting smaller and smaller and smaller each time. And then to the left of the binary point, again, we've got our normal binary digits as per usual. And by combining these values together, we can represent different fractions. So in other words, just like by combining these bits together, we can come up with different combinations of whole number. Here, by combining these values, we can produce different fractions. So an example is here is 5 3/4. So if I want to represent 5 3/4, the 5 is just 4 up 0 1 as usual. Sorry, 1 0 1 as usual. And then to come up with 3/4, a half and a quarter added together is 3/4. So it's 101.1100. So again, a good time just to have a little pause just to make sure that that makes sense to you, but hopefully it does. So again, a question that we've asked a few times in this topic: can you see potentially a difficulty or a problem with this method? And I suspect, probably bearing in mind what we looked at with sign and magnitude. Okay, so the difficulty is really very similar to the problem that we saw with sign and magnitude. In fact, we've got two possible problems. We've got limitations of both the range of binary numbers that we can store as fractions and the accuracy of the binary numbers that we can store as fractions. So if you look at our scale here, remember we have these 4 digits available to us, these 4 bits to represent the range of the number. So we've now only got 4 bits in which to store a value. So what's the largest number that we can put into 4 bits? And then we've only got, in terms of the accuracy or the precision of our number, these bits to the right hand side. Now, it's not so much, we could obviously have a 16-bit number or a 32-bit number, but we're still going to have some issues with accuracy. So if you look at this table is in your book, and obviously we don't expect you to remember it, but what you can see each time is that this is getting smaller and smaller. It's basically half the size each time. So you've got what binary places look like in a binary fraction, starting with 0.1 going all the way down to here as binary fractions, and then as decimal fractions. So starting at half and moving all the way down to 0.0039065. And what you've probably realised, well, in fact, before we mention that, we'll just do a little conversion. So if we want to convert though from binary or from decimal to binary, if we want to do a binary fraction, it's actually really straightforward. So here is a normal decimal number, decimal fraction, 3.5625, and we've got 4 bits to the right of the binary point. So you should always assume that unless it says otherwise. And I've included the table, part of the table from the previous slide. So how would we do it? So this is what we do. First of all, we would take 0.5625 and subtract a half from it, or 0.5. Okay, and then because that's our first bit in the fraction part of our number, and that would give us a 1. The reason it would give us a 1 is because we are able to perform that subtraction. It doesn't give us, it's not the result of the calculation, but we put a 1 there if we are able to subtract and a 0 there if we can't. So we can subtract this half from that, and that gives us 0.625. And then we begin with that digit, 0.625, underneath here. So we take 0.625 and then we subtract the second place of the decimal fraction, 0.25. Well, we can't subtract 0.25 from 0.625, so as it won't go, we put a 0 there. So then we carry the 0.25 down to, sorry, the 0.625 down to here. That number hasn't changed because we've subtracted nothing from it. 0.625 minus 0.125, that's the third place on our decimal fractions kind of table here. And again, we can't subtract 0.125, so we put a 0 there. And then the final bit that we do, that should say 0.625, not 9.625, sorry. 0.625 minus 0.625 is 0. So you can take 0.625 away from itself. I will change this so that by the time you see the presentation, that will be a 0, not a 9. So you can take 0.625 away from itself, and it ends up with 0. But because the subtraction can take place, you end up with a 1. So essentially, what you would then do, that gives you what the fraction part of the number would look like, 1001. And then it's just 311.1001. So 0011 dot 1001. So that's slightly tricky, perhaps slightly confusing, because it's just something you need to practice, really. So there are some practice questions for you to do to get the hang of this. So each time here we get the 1 signifies that we can perform a subtraction. It doesn't mean that 1 is the value of the subtraction. So we're nearly done now, and the only thing really just to point out is that one of the limitations of this, hopefully it might even have become apparent while you're doing this sum. If we go back to here, this question of accuracy, is that there are going to be some fractions that we just cannot represent using this system. So for instance, 0.3 is impossible to represent accurately in binary. 0.4 I think is another number that we can't accurately represent in binary due to the limitations of this. So fixed point binary numbers are easy to work with, straightforward to work with, but they do present us with an issue in terms of the range and the accuracy. How do we overcome that? That's something that we're going to look at in year 13 when we look at floating point binary. But really, that's just a short introduction to binary and decimal fractions, and hopefully that's made some sense to you. So that, ladies and gents, is all. That's everything that we need to cover in this particular lesson. And I've put 3 quotes so you can scan these directly with your phone if you want to, or actually I've included links to the documents on the website, and they're in the relevant slide on the website as well. So there's plenty of ways you can access these. There are some written questions covering the 2's complement binary subtraction and binary fraction conversion that you might want to have a go at. There's the answers to those questions so that you can check. And then there's some multiple choice on fixed point binary as well that you can have a go at. So try those, and then if you need to review the presentation, do so. If you need to review any of this video, please do so, and we can have a conversation about this to make sure that you've understood everything that we've covered and that it makes sense. So hopefully this was okay for you. Please let me know how it works if you've got any questions, and I'll speak to you again